All right, hello everyone. Welcome to the PEARG Privacy Enhancements and Assessments Research Group. My name is Chris Wood. I'm here with Siobhan Sahib. Sarah is with us remotely and Meet Echo. Just quickly moving forward. This is the note well. You've probably seen this lots of times so far, but if you haven't, please take a moment to familiarize yourself with it. Or you can read it online. Siobhan is passing around the blue sheets. Please make sure you sign them. We have a Jabber scribe, correct? Yes.
Is Mallory here?
No.
Do we have a Jabber scribe? Is someone willing to be a Jabber scribe?
Do you want to do just Jabber? Which one would you prefer? Okay, let's do Jabber. We also need a minute taker then. Any volunteers? Make eye contact with people I know until someone nods their head. Ben, thank you. So this is the agenda we have today. We have 80 minutes of sort of researchy presentations to start. And then followed up by some proposed individual drafts for the research group to close things out. Does anyone have any last minute comments, revisions they would like to make before we get started? Doesn't look like it. Okay, so on that note, we will kick things off with Pete, who will tell us about privacy standards and anti-standards. Right next, actually.
Cool. Hi everyone. My name is Steve Snyder. I'm from Brave Software. Sorry.
You might need to talk closer to the mic.
Thanks a lot. Okay, take two. So my name is Pete Snyder. I come from Brave Software, where I do privacy research. I'm also co-chair of PING, which is a privacy group in W3C. And so this is some lessons taken away from the intersection of those activities. So just as a brief overview of what I'll be talking about, first I'll talk about how standards impact the privacy work that Brave does as a privacy-oriented vendor. Very briefly, and then I'll give a couple of examples of anti-patterns that we see reoccurring in standards and how that makes life difficult for people who want to do privacy protections on the web. And then finally, I'll give just some kind of list of additional topics that are related that I would, I think, warrant further discussion, but there's not time for it in this talk. So first, how do standards influence or impact our work as a privacy-oriented implementer? So in order to protect privacy on the web for our users, Brave makes a bunch of modifications to the browsing environment. We block state storage in different places. We integrate Tor and allow users to use Tor out of the box. We block a whole bunch of resources from being loaded in the first place from a variety of different places like EasyList and in-house generated lists and things like that. But most relevant to this conversation is we modify the browser environment. And so we end up violating standards in a large number of places because implementing those standards correctly would harm our users' privacy. Just to give kind of a very specific example, here's a recent paper that came out that gives an overview of a bunch of fingerprinting methods that are done on the web. Relevant to this conversation is not only do they do a nice job of surveying existing work on how people are actually being fingerprinted online, but they also give the impact of each of those fingerprinting methods and kind of how much identifying power they give. And so the one I want to talk about here is on the right-hand side, audio context, which is a way of identifying the user based on particulars about how the browser will do audio synthesis. It turns out, I won't go to the details, but it turns out that different vendors and different pieces of hardware and things like this will do this very subtly differently, or sometimes not so subtly, and you can use this to build up a semi-identifying piece of information about the user, which can be combined with others to uniquely identify them. And so Brave modifies this, and what we do is we null out a bunch of things that the browser allows you to do by default. These are things like querying the hardware for its capabilities or different low-level things. And so what Brave does is we just say no. When it's in a third-party context, we just say you can't do that unless the user opts in explicitly. This violates the standard, but to do so otherwise would allow our users' privacy to be harmed. We do this in a whole bunch of other places as well. This is not even nearly a complete list, but I mentioned these just as a partial enumeration of how extensive the problem is. So how did we wind up in this situation, or why is this problem so endemic across the browser platform? I'm going to give 3 different examples of these kind of anti-patterns we see in standards that lead to this outcome. This is not anywhere near an extensive list or a comprehensive list, but I mean it as motivation and demonstration. So, also, I don't mean this to be simple. This is not like just do these 3 things and all of a sudden privacy becomes easy, but I mean them as a necessary but not sufficient list of problems. So first is we see reoccurring over and over again that standards are extremely specific about the functionality that needs to be implemented, but are extremely unspecific about how to mitigate the privacy harm that functionality adds. So, for example, many W3C documents have a privacy consideration section. These are things saying like implementers should be concerned about these privacy concerns when they implement this, but they are not normative, they are not mandatory, they are just a list of concerns. But the rest of the document, which is almost without fail, much longer and much more specific, says specifically the functionality that must be implemented. And the result is that everybody implements the harmful part, and people are extremely unsure what to do about the non-harm or about the mitigating part. And as a result, vendors' hands are tied when they want to try to do the mitigations because websites assume the well-defined behavior. So just as a motivating example of this, one you may be familiar with, refer policy is a standard that says, under certain conditions, notify the website that you're visiting now of where you just came from. This has extremely specific, very obvious privacy implications. There's a very short piece of text saying, we know that there's privacy problems here. But in the mitigation section, it just says vendors can do whatever they want. There's no specificity. It just says vendors may violate this at any time. As a result, many websites rely on, this is very unuseful to website operators, and as a result, many websites just assume the refer policy will be standardized as it's described in the rest of the document. And now if you're in Brave's position or somebody like Brave's position where you want to protect the user's privacy and you remove the refer header, or you do different things to try to make the refer header less privacy harming, you break a whole bunch of websites.
Sorry, can you step back, please?
Oh, sure.
This text seems to explicitly permit user agents to suppress the refer header entirely. What would you want it to say?
I would like it to, well, I have a long list of things we could probably talk about offline, but to the first high order bit would be, don't do this. But if you had to do it, I would say, don't expect it in third-party contexts. Refer policy should only be sent on, or refer header should only be sent on a user gesture, things along these lines.
I think you have okay. Well, the last point is different, but I think you have an extremely optimistic view of the degree to which web authors read specifications. Website users know what Chrome does.
I think those are probably, I'm sure you're right that web authors do not read specifications. I'm sure that web authors do read things that are distilled from specifications frequently.
Perhaps. My experience is they do what Chrome does. So, so I guess my point is that your thesis seems to be that it's flexibility in the specification that creates the problem. I'm not sure making a very persuasive case for that in this particular example.
I think that may distill down to a distinction without a difference in that by saying vendors can do anything, everybody is following the specification, and so Chrome is following the specification and also doing what the web follows its lead. The standard is no longer the guiding principle is what I mean.
We can take this on.
Sounds good. Okay, example 2. Functionality that's useful only in a very small set of situations, but is made universally available to all websites. So the problem here is you have something that's very useful to a very small number of people. Maybe that's doing things like audio synthesis, but it's made without, there's no permission in place. There's no gating the functionality, no anything like this. And so all of a sudden, it's not being used just for this very narrow use case. It's being used for fingerprinting, or it's at least available for fingerprinting. It's available for these kind of privacy harming uses. And so as a result, it becomes extremely difficult to pull this off the web without breaking a whole bunch of websites that expect it to be in place. An example here, Canvas element allows you to not just write things to the canvas, but also pull things out. The use case for this is not zero, but it's obviously not the common case of when you're writing things into a canvas. And so what do we see? We see the common use case of this is on libraries like Fingerprint.js2, where if you dig into the code in the lower right-hand corner, you can see this being used to generate unique identifiers for users. Now, if you pull out, if you think you're somebody like Brave, or you're somebody who's doing privacy protections, you think, great, we'll just pull out this functionality. Well, now all of a sudden you've broken a whole bunch of useful use cases as well, where the permission, the goal in the first place should be just to say, figure out a way of gating permission to gating access or restricting access to these kinds of positive use cases in the first place.
I'm sorry, me again. How would you do that?
So again, I have a long range of suggestions, but the first approximation is to say user gesture, to say permission, to say some other way of the user signaling I like to do a thing.
I'd like to, what, have you read back Canvas?
Likely, so reading back canvas in and of itself is often not useful. You need to do something with that value for it to be useful, save it to disk, save it to storage, something like that. And so those are things that other browsers already gate behind these sorts of things, storage access API, what Brave does, et cetera. And so these things get paired together, and it'd be natural to pair them in that way explicitly.
Yeah, I think the problem is, it seems to be going to a place where we're going to be constantly prompting the user for like all sorts of things they can't possibly give informed consent to.
Permission prompts is one of these things. User gesture is not a permission prompt. Third-party frame is not a permission prompt. Things like that.
Sure, but user gesture, sure, but like not everything can be sensibly behind user gesture. Like lots of things, like in particular for canvas fingerprinting, there are plenty of ways to force the user to produce user gesture, right?
It is not possible to trick the user to do many things, but requiring the user to do something would take it out of the common path for sure.
Some common paths.
So these are additional lists of things that it's extremely hard to think of why every single website needs ungated access to them. These are all things that are used in fingerprinting techniques, and I would suggest we should do something similar here. So what's the lesson to take away from this second pattern? Assume that people will use your functionality if you allow them to use it across the board. If you think there's only a small subset of use cases or places where your functionality is actually needed, figure out ways of gating or restricting accordingly. Okay. Third and final is what we see over and over and over again in standards conversations, which is websites can already do bad things. What is the marginal harm of allowing them to do an additional bad thing? I think this is unhelpful. So for example, if a standard is proposing a new way of allowing web servers to do applications to do communications to remote servers, the common refrain is you can already do it with an image tag. What's the harm of allowing them to do it in a different way? This is a way of expanding your horizontal privacy debt indefinitely and making it impossible to fix the problem after the fact. An example here is client hints, which is both has aspects in the W3C and IETF. The relevant part here is, I won't walk through this because I assume people are familiar with since it lives here. But there's a large amount of papers being written and research that exists showing that the exact kinds of values that can be requested through client hints can nearly uniquely identify a non-trivial number of users. As a result, the response is often, well, you can already identify users anyway. What's the harm of already doing this? Cookies exist, don't they? Et cetera, et cetera. I think this is a way of just doubling down on the problem. To put it differently, when you're digging, stop digging. Or when you're in a hole, stop digging. Freeze the problem, start figuring out ways to mitigate the problem as is, and don't entrench the problem indefinitely. Again, I'm happy to say more specifics if this is a topic of interest. Yeah. Okay, one last thing I wanted to say is just kind of bullet point of a number of different things that I think would warrant further conversation, but are too much to go through in detail here. one thing that we see over and over again is a way of kind of pitching the problem forward to say, we know this new standard introduces a privacy harm, but we're working on the standard that's coming down the pipeline in the future that will fix that problem. I think this is extremely harmful. Not only does it tie the future author's hands in what now they have to do to redress the current problem being introduced, but it gives you it makes it extremely difficult to evaluate the privacy harm by the standard you're considering right now, which is to say something may change in the future. That is not a basis to judge something that's going to be introduced today. Second point I think is worth keeping in mind when evaluating standards is that the idea of formalizing bad practice has at least some appeal in that you can say, well, if we can get all the bad uses to use this new API instead of the old API, then we can reason about that new API use in some semantically valuable way. I think this is not useful because what ends up happening is bad actors use both APIs instead of just a new one. And then last is this kind of, what I think is this kind of like judo move where people say, well, site authors use this, people like sites, and so users indirectly want this to exist. I think this is totally not helpful. It is important to consider the site author's needs, but first and foremost is the person operating the software, and to recognize that those interests diverge frequently, and to consider the harm to the user, not to nebulously users in general. So some last takeaways, some last things I hope to keep in your mind is that the amount of standards getting pushed through is just extremely difficult to be able to reason about privacy-wise. And so to a first approximation, the best thing we can do for privacy is to just slow the roll a little bit, and to give things a little bit of time to percolate and to percolate through the review processes. Second, to think about complexity in and of itself as a privacy harm. It's not adding anything new to the platform brings some risk. It also brings some reward, but to not think of it as there's no privacy harm that I've identified, so it's fine to add it, is not the right criteria to consider when you're thinking about improving privacy on the platform. And then third is, I think, a totally under-considered risk is that standards work largely now, or a non-trivial amount of standards work is standardizing things that are already shipped. And at that point, it's nearly impossible to pull them back in. And so figuring out some way to reason about things before they get off the door, or at least earlier in that process, is probably a place worth digging into. Okay, so I'm happy to discuss any things more, but I just want to say thank you very much for your time. I'm Pete Snyder. I'm the privacy researcher at Brave. And I'm here to try to help do better in privacy as standards. Thanks.
Are there any questions? No. So I have one. Pete, you mentioned many examples in which standards could potentially be improved, or specifications could at least be potentially improved to help, perhaps benefit the privacy of those implementing them, or those users that are using the things that are implemented. Is there any, what sort of concrete or tangible steps can either the IRTF or the IETF take to move in that direction? Maybe you can offer some advice, or I guess,
sure,
next steps.
So I think there's in W3C we have the idea of horizontal review boards, or horizontal review groups, that at different iterations in the standard's lifetime, from conception to recommendation, groups like Ping, the privacy group, but other groups like accessibility are expected, or at least have the option of giving input at that point. I think formalizing that process stronger would be an extremely useful way of allowing interested and concerned actors to get involved earlier in the process.
Stefan, sorry.
Stefan Bartsmeyer. Most of the examples that you mentioned were taken from the world of W3C, which I'm not familiar with. Beside the client ints, do you have ideas of protocols, IETF protocols with the same sort of problem? Because in theory, in the IETF, people should write security considerations, including privacy. We have RFC 6923. So in theory, problems should not happen in the IETF, but of course they do. So do you have specific examples in mind from your experience with the browser?
So I don't have any examples from the IETF world specifically that I would feel very confident talking about beyond just kind of, from the outside. But I would say we also, so W3C standards also have these privacy and security consideration sections. And as a concerned vendor, I think that is a step one of what needs to be a 10-step road.
Ted?
Ted Lemon. So thanks for presenting this. This is really helpful. One of the things that I've noticed people do to try to mitigate risks of this sort is to have essentially a list of things that a particular site is allowed to do. And that seems like, I mean, this really wouldn't apply to IETF standards, but it sort of seems like it applies to the stuff that you're actually talking about here. So basically a set of entitlements. I mean, does that make sense to you as a way? Because the problem with what you're with slowing down the advancement of progress, so to speak, is it's very difficult to do because there's always somebody who wants this new feature. And what do you say to them? I mean, the new feature is probably totally privacy violating, and there really isn't a mechanism for actually preventing it from being exposed to the user when the user doesn't want it to be exposed to them. There's no way to actually enforce that restriction. So it seems to me that the actual research problem here is how do we create a framework for enforcing restrictions of that type?
So I completely agree with you that figuring out what sites should be allowed to do what at any given point is extremely difficult. I slightly disagree with you in that there's not ways that vendors can enforce those choices. Those vendors, a couple of examples came up before. Other things may be policies determined by the browser offline or shipped with the browser given some known set of safe sites. Permissions are a knocked around but not useless way of going about this. User gestures where the frame is, where the code came from, which is not a variable in any standard currently, but not what frame is it executing in, but who delivered it, et cetera, et cetera, et cetera. So I think there's more avenue there for hope than.
Well, it sounds like you actually agreed with me there, because what you're really saying is that we need a way to make that happen.
Oh, yes, I definitely agree with that. Yeah.
Thanks.
Gary Mundy, I'm Qualcomm. I recall back to 6 years ago when I was chairing the geolocation working group in the W3C. We had a discussion related to ping advice on the topic, and we discussed the concept of whether a web page could, or a web service provider could declare to the user what their intentions were as far as any information that they would provide. And we couldn't figure out a way to actually do that without without it being abused by rogue parties. I'm wondering now, though, when you look at innovations such as certificate transparency, and we're getting better and better authentication into the browser all the time with respect to websites, whether browser-based policies with respect to individual websites could actually take the place of having to specifically advise the user from the service itself. So I was wondering what your thoughts were on this.
Well, I mean, I think geolocation in the browser is actually a positive example. I mean, that is of the many ways that user privacy is harmed, that is not often one of them, because it very explicitly says users understand what that means and they opt in. When I think of the 100 things that makes me concerned, that's not one of them. I think for specifically that reason. I think the idea, I'm not sure there's any solution to the concern of the website saying, I'm only going to do this with that information. I think that's probably, even given in other advancements, I think that's probably not a way that is going to be useful going forward.
Oh, thanks, Pete. Thanks. Moving on to the next presentation.
Yes.
You want to just hold it?
Can I? Is this clear? Okay, yeah. Okay. Hi, everyone. I'm Sandra, a PhD student at EPFL, and today I'm going to present some work done by myself and my co-authors on traffic analysis of encrypted DNS. So I'm going to start by jumping straight to our conclusion, which is that we did a number of experiments where we did a traffic analysis of DNS over HTTPS traffic, and we found that monitoring and censorship are still feasible even in the presence of encryption, and that currently proposed eDNS-based countermeasures against traffic analysis are not sufficient to prevent such attacks. So in this talk, I'm going to describe some of these experiments in detail. So when a client connects to a destination host, generally this is preceded by a DNS lookup. As we all know, there are measures in place to encrypt the connections between the client and the destination host. But DNS lookups have so far been sent in the clear, which makes them susceptible to eavesdropping and tampering. For example, if you have an adversary on the path between the client and the recursive resolver, the adversary gets some idea of the browsing history of the user, for example, which is a privacy concern. There is also censorship that's based on DNS. So there have been measures in place before that have been proposed to improve DNS security. You have measures such as DNSSEC, which look at authentication but do not provide confidentiality. And you have measures such as DNSCrypt, which allow for encryption but did not see much widespread adoption. Over the last couple of years, you have these protocols DNS over TLS and DNS over HTTPS, which have been gaining some traction. The idea behind them is to set up a TLS session or an HTTPS connection between the client and the recursive resolver and exchange DNS queries and responses over this connection. And since this is encrypted, ideally this should provide some privacy for the user. So the scenario that we are looking at is an observer who is monitoring the connection between a client and a recursive resolver. So the user visits the page and the observer tries to get some features from this DNS over HTTPS or DOR traffic and tries to guess which web page is being visited by the user. Note that since the connection is encrypted, the observer no longer has access to the content of the DNS queries and responses, but looks at information such as sizes of packets, the timings between the packets, the directionality of the traffic, or headers such as TLS headers. And the idea that we're basing our analysis on is the fact that when a user visits a web page, there are a lot of additional resources such as ads, static files, or images that have to be loaded as well, which could be hosted on different domains. So a visit to a web page actually consists of multiple DNS queries and responses, and the set of queries and responses could act as a fingerprint for identification of that web page. We are considering two adversary goals here, monitoring and censorship, and I'm going to speak about each of them. So as I mentioned before, the goal of a monitoring adversary is to look at the DOH traffic and get some features. So I try to identify the web page visited by the user. So for this, we build a classifier based on size and directionality features of the DOR traffic. I don't go into the details of the classifier. They're available in our paper. But we basically conducted two experiments here. In the first experiment, we considered a case where an adversary knows the entire set of web pages that a user has visited. And the goal of the adversary is to identify which particular web page was visited by the user. So in this experiment, we considered a set of 1,500 web pages. So if you consider a random classifier that tries to guess which web pages it is, the classifier would try to guess this with 1 on 1,500, basically. But what we see is that our classifier gets a 90% precision and recall, where precision is a measure of correctness of all the results that were returned by the classifier, and recall says how many relevant results were returned. So when the classifier has a high precision and recall score, this means that not only did the classifier identify a large number of web pages, it did so correctly. In the second experiment, we consider a bit more realistic scenario where an adversary does not know all the set of web pages that are visited by the user. Rather, the adversary is interested in a subset of the web pages called the monitored set. And the goal of the adversary is to determine whether the user visited a page in this monitored set. So for this experiment, we looked at a set of 5,000 web pages where 1% of the web pages were in the monitored set. This is generally a harder classification problem in the area of website fingerprinting. And we see that we get a lower precision recall score of about 70%, but this is still much higher than a random case. The second goal that we considered was censorship. We did a preliminary analysis of a censoring adversary. The goal of a censoring adversary is slightly different. The idea is to identify a web page as fast as possible and ideally try to block the connection. So this means that an entire door trace will not be available to the adversary, and the adversary has to look at partial door traces. So what we did here was we took a set of 1,500 web pages, and we looked at the uniqueness of the door traffic when only the first LTLS records have been observed. And the idea behind this is that when two traces are unique, then we can find out which trace to block. So what we found out in our analysis is that generally the fourth TLS record usually corresponds to the first door query in our traces, and the size of the TLS records also has connection to the length of the domain name. So this means that one strategy that an adversary could follow would be to block on the first query. This means that the user will not be able to load the page. The disadvantage of this method is that it could result in high collateral damage because other pages with the same domain length could also be blocked as a result of this strategy. Another thing that we found out was that by the 15th record or so, which corresponds to approximately 15% of a trace length, most of the traces in our set were distinguishable. So the adversary could follow a strategy where they try to block after having a high confidence that this is the trace that they want to block. So this reduces the collateral damage, but the disadvantage is that this would result in the user being able to load most of the page. They might miss out on some of the resources of the page. We also did a number of experiments where we looked at the robustness of the attack. And by this, what I mean is when different aspects of the experimental scenario change, how does the adversary try to keep good classifier performance? For example, DNS traces can vary over time. So how often does the adversary have to retrain their classifier? Then we wanted to see the effect of client location on our classifier, as well as changes in the infrastructure. So by infrastructure, I mean we changed the resolver. We experimented with Cloudflare and Google's resolver. We looked at Cloudflare's standalone door client, as well as Firefox's inbuilt client. And finally, we did some analysis of desktop versus Raspberry Pi environments. And the main takeaway is that for best performance, ideally, you would train a classifier that is tailored to that particular scenario. If you use a classifier trained on one set of parameters, the classification performance does drop when you test on another set, but it does not stop the attack. So what we saw from our initial set of experiments are that monitoring and censorship are feasible even when DNS traffic is encrypted. So we looked at countermeasures to prevent traffic analysis attacks. So the first thing we looked at was Edn Airspace Countermeasures, where EDNS is extension mechanisms for DNS. So one of the options in EDNS is a padding option, which allows you to add some padding to DNS queries and responses. And the idea behind this is that you remove the size information that is available for the classifier to distinguish web pages. So the first thing that we did was we implemented padding of DNS queries. So we used Cloudflare's standalone door client for this, and we implemented a recommended padding strategy. So the RFC there has padding strategies, and the recommended one is to pad queries to multiples of 128 bytes, which is what we implemented on Cloudflare's client. We had also contacted Cloudflare with the initial set of results, and they implemented padding of responses on their resolver. However, they padded their responses to multiples of 128 bytes, whereas the recommended strategy is to pad them to multiples of 468 bytes. So we decided to compare both the strategies as well. So the experiments that we did were the two EDNS-based measures, which I just described. We also looked at a case that we call constant padding. So this is a simulated scenario. We wanted to see if we had perfect padding, that is, if all the TLS records were kept to the same size, how the classifier would perform. So we basically set all the sizes to the maximum possible value that we saw in our trace and applied the classifier to this case. And finally, Cloudflare has a DNS over Tor service where DNS queries and responses are sent over the Tor network. So we decided to experiment with this service as well to see how anonymous communication acts as a defense. So this table outlines the performance of the classifier. Just note that the values are as decimals, not as percentages here. For comparison, without any countermeasure, the classifier attains about 90% precision and recall. We see that with EDNS, with the current Cloudflare strategy, precision and recall drops to only about 70%. With the recommended padding strategy, it drops to about 45%. Both these values are much higher than a random case, which shows that EDNS-based measures do not eliminate traffic analysis. If you look at constant padding, it's about 7%, so there is a major drop in the performance. And DNS over Tor achieves the best results with about 3.5% precision recall. We also looked at the overhead in terms of amount of additional traffic that is added by these countermeasures. So we did a very short experiment where we took 50 web pages and about 6 samples per web page and applied each of the countermeasures and looked at the total volume that is sent and received bytes of the TLS records. Just note that the y-axis is in log scale here. We see that the EDNS-based measures, as expected, do not add much overhead. However, constant padding adds a lot of overhead because we are padding everything to the maximum size, and DNS over Tor is somewhere in between. So we see that Tor is effective defense for the traffic analysis attacks. And the reasons are that in Tor, you have the data sent in fixed cell sizes, which reduces the variability of sizes and affects the size-related features of the classifier. Another thing is that there's repacketization, and by that we mean the data can be merged or bundled together in Tor, and this affects the directionality features. We look at which records have been sent and received, and when Tor does this, this affects the directionality features used by the classifier. One thing that we are not being able to explain are the clusters that we saw in the confusion graph. So this graph shows web pages that have been mislabeled as one another. And what we saw is that web pages generally tend to be clustered, where web pages within the same cluster tend to be misclassified as one another. This means that the anonymity set for a particular web page is not the entire set of web pages in the test, but rather only the web pages within a particular cluster. So we did some initial traffic analysis, but we have not been, feature analysis, but we have not been able to determine why this is the case. Oops.
So I can take this opportunity to ask a clarifying question as long as you're waiting.
Yeah, sure.
Is your Tor protection, is that DNS over DOE over Tor, not DNS?
Is DNS over Tor.
So regular DNS?
Yes.
Okay, thank you.
Over Tor. Yeah, inside Tor.
So one of the ways of getting help is, it's back. Okay.
Oh. Plug it back in.
Okay, so you may as well finish your last slide, I guess.
Should I complete first? Yeah. Oh, okay, sure. Yeah, I'm on my last slides anyway. So currently we are working on a few different things. The first thing is that our experiments looked at the case where a user is visiting one page after the other, and this is not exactly a realistic user scenario. So we are considering the case where you can have multiple tabs opened by a user, which results in some interleaving of the door traffic. Our initial results show that our classifier gets about 40% precision recall with about 2 tabs. Another thing is that we consider the case right now where there is no caching of the DNS records. So we want to study the impact of caching as well on the classifier. We also started doing a comparison with DNS over TLS traffic. And we looked at the padded DNS over TLS traffic, and we see that it is much more resistant to the classifier. It's about 28%. As compared to DOE. So we've started doing a feature analysis to see why this is the case. And finally, we want to see if we can have countermeasures which include both padding and repacketization, but without TOR's overheads in latency and volume caused by headers. So this is basically the summary that currently proposed eDNS measures might not be enough to prevent the traffic analysis. And these are some links to our paper. Thanks.
Let's get started with questions. Stephen.
Yep, Stephen, I think really good work, thanks. If you go back to the table.
Yes. This
yeah.
one? Yeah.
So I saw when you say constant padding, I had a quick look at the paper, and I mean, you padded to the biggest sized packet of all.
Yeah, so this is, so we don't actually apply the padding here, but what we do is we take all the traces and we change the sizes to the same value, which is the largest value that we saw in the set. Because the idea is that you want to see a perfect scenario where all the sizes are the same.
Okay, so when you said constant padding there, it doesn't mean just padding every TLS encrypted.
Oh, no. No.
Everybody gets to be the
yes.
maximum size.
Yes.
Okay, got
yes.
it. Now, nonetheless, why is that so different from EDNS 468, do you think? I don't understand why doing that makes such a difference.
Well, when you do for EDNS 468, what we saw is that there is still a variability in the sizes that are there in the class. And the variability in the sizes is a big a feature for the classifier. Whereas with constant padding, because all the sizes are the same, the size is no longer a feature for the classifier.
This is in variability in response sizes, I guess?
This is both query and response sizes.
So you had a lot of queries that were where 128 is not enough padding, is that right?
Yeah, but I just want to clarify that the response sizes have a greater variability than the query sizes, so the responses do have a higher impact than the queries.
And were you able to determine what is it in the responses that's causing them to go more than 468? Is it DNSSEC or?
No, we haven't yet done that analysis of the content of the responses.
Okay.
Yeah.
Great. So I think that's an interesting difference, and finding out more about that and turning that into some guidance for people, like, presumably somebody's using like a really known query name, so don't do that if you don't want to be, and somebody else is giving like lots of answers. Yeah.
Hi, Daniel Kahn-Gilmore. Thank you very much for doing this work. I am the guilty party for proposing EDNS 0468, and I propose it specifically because I wanted to encourage this kind of work. So I'm really happy that you've done it, and great to see the results. The way we arrived at the recommended padding policy was basically to look at individual DNS queries and responses. And I like what you've done here, which is to look at them in combination. So I have a couple of questions that maybe you can give me what your intuition is. I think what you're saying with the constant padding arrangement is that the reason that it's not 0 there is that different websites do different numbers of DNS lookups.
Yeah, so there are a couple of things. It also depends on the kind of features that we used. So one of the things that we looked at was, so if you have a trace, we looked at whether each TLS record was going from client to resolver or from resolver to client. Okay. So then you have basically a sequence of, which direction it is going in. So even if you remove the sizes, you still have this directionality as a feature.
Directionality and also parallelism, right? If I issue 3 requests and get
Yes.
3 responses back,
Yes.
that's different from saying request, response,
Exactly.
and then request, response. Okay,
Yes.
So number of queries and cadence.
Yes.
Sort of.
Yes.
Okay. And then I wanted to ask you to hypothesize. I know you haven't done the research to dig into it and produce a printable result, but why you think the DNS over TLS was markedly better than the DNS over HTTPS?
So, I mean, if we looked just at the sizes, we saw that there was much less variability in sizes. I'm wondering whether it is due to some of the configuration messages that are being exchanged in DO in addition to the queries. Like we don't distinguish those messages since we are looking at just the TLS record sizes.
You mean like an options frame?
Yeah, maybe something like that, which could be different for DO and TLS.
Okay. Thank you very much for doing this.
Thanks.
Hi, Rowan Straussek in Eld Labs. Very cool work. I really appreciate that. So one question has already been asked because TKG asked it. But the other one I had was, so there's this hypothesis that the DO specifiers have that if you mix DOH traffic with normal web traffic, that would obfuscate the signature of the DNS traffic a lot more. Is that something that you consider studying as well?
Yes, this is something that we thought about. Right now, we do consider DO traffic as separate from website traffic, and we feel that when you mix them, this might affect the results. We haven't done some work on that yet, but this is something we're considering as well.
Okay, thank you.
Yeah.
Wes Whitaker, ISI, and he took my question, so I'm going to ask the little tiny one at this point. Is your data set available?
Yes, we're planning to make our, it's not available at the moment. We're just sort of cleaning things up and we're planning to make it available soon.
Awesome work. Very
Thanks.
Christian Wittemer. I am curious at how exactly you measure the length of the queries and the responses.
The lengths of the queries and the responses. So we get PCAP files and we look at TLS records which are of type application data, if I remember, and then we take the sizes of those TLS records.
So you assume that there is a direct mapping between the size of the DNS messages and the size of the TLS records.
We also did verify this by decrypting the records, and in our paper you can see we have a plot where we show the sizes of the queries as well as the sizes of the records, and there is they follow the same shape essentially.
So what if an implementation was not was deliberately either grouping several queries in the same record or splitting queries in multiple records? What would that do?
Groupings, queries in the same record, or I think that queries. You mean it changes the size of the record?
Well, suppose that you have 5 queries, for example.
Yes.
There is nothing in the protocol that says that those 5 queries have to go in 5 TLS records. They could be packed in one big message.
Yes.
That is sent as a single TLS record.
Yes.
So if site did that, would that change your results?
I think it might change, especially if the classifier has been trained in a particular way, as in if it's trained based on traces where individual queries are in individual records. This, of course, changes the pattern of the traffic. So, however, if you train it in that particular case, if you have a mix of traffic, I think it would affect the performance of the classifier. Yes.
Thank you.
I'm Jeffrey Yaskin. Do you have any feeling for how the precision and recall will scale as you increase the universe of websites from a couple thousand to the size of the internet?
So this is one of the major things because our data set is not very huge. We rather have multiple experiments with smaller data sets. I would assume that the precision and recall would go down but I don't know by how much. Yeah.
So this is Sarah Dickinson on Jabber. She asks, have you considered including oblivious DNS in a future analysis? And yes, actually, Carmela, I think your colleague already replied, but
Okay.
if you want to add something. She said, that was not on the plan, but it could be. Can you give us, she asked for an implementation link, but yeah, if you have anything to add.
For oblivious DNS?
Yes.
Maybe correct me if I'm wrong, but oblivious DNS has a slightly different adversary model, right? Where the idea is that the recursive resolver does not, there's no mapping between the client and the query. And we're not looking at on-path traffic, but.
I don't know enough to answer this question.
Okay. But yeah, we haven't considered it yet so far.
Hi, very nice work, Giovanni
Thanks.
Saiyan. Did you consider like to emulate the behavior of a national security agency or something like that, intelligent agency, that you have a set of websites that you know they don't want you to go to, and then so you try to fingerprint them with whatever your method is, and then you get like domain names from various lists or entire DNS zones and try to see if an experiment like that you would be able to detect them, like detect users going to those allegedly forbidden websites.
Sorry, just to clarify, your question is whether we are going to analyze such a
Or if
scenario?
you consider, or if you plan, or would be an interesting idea, or you have any thoughts if you would be able to detect that?
Yes, so as I mentioned in like our censorship related work, like we have done a preliminary analysis at the moment, but we are thinking of continuing in this direction and seeing how, if, whether we can have a set of websites and if the user can visit those or not. Yeah.
Okay, cool.
Thanks.
Hi, Riyad Wabi. Nice work.
Thanks.
Have you considered, are there extra features that maybe you're leaving precision and recall on the table? So for example, what about inter-packet arrival times?
Yes, so we did an initial feature analysis and we did consider inter-packet arrival times. At that time, we didn't see that it increased. I mean, it did increase the precision recall, but not by much. And usually we found that using timing as a feature can also be complicated because it also depends on which position the adversary is, whether, we are locating the adversary on a router or no, if we are doing measurements right on the client or not. So that's why we decided not to do the timing based features. But our initial sort of analysis did show that including the timing can raise the precision and recall by a little bit.
Thank you.
Thanks.
Thanks a lot, Sandra.
Thanks.
Next up, we have Chris.
All right, so this is going to be I'm going to truncate this presentation because a lot of it overlaps with what was just presented. Thank you very much for giving everyone the background necessary. This is joint work we did with Nikita Borisov and Simran Patil. It was presented at the ANRW workshop earlier this week. And so just to get right into it, as you may know, and as was just described, there's a recent shift in focus on privacy in the IETF and IETF in general. In particular, we're trying to protect what resources or what applications or what services particular clients are using, and there's also I guess the converse or the opposite side of that is what we're trying to protect, who is accessing these particular resources and using these services in connections and whatnot. Clearly, the former is easier than the latter. Or rather, the former is harder than the latter because we have very distinguishing identifiers currently, like IP addresses and other things that are in client software. So that's what I'm going to focus on. And the IETF has been trying to do a lot of work to push in that direction, in particular, rolling out DOE and DOT and TLS encrypted SNI. All of these things are, plugging the various holes that have come up over time or that have existed for a very long time in hopes of, eventually masking what is the client actually up to on the internet. So in this particular model, we're concerned about the privacy of a particular connection that is used to request a particular resource. We're generally assuming an adversary that's local and passive. It can observe all packets between the client and the server. And the goal is pretty simple. It just wants to learn some information about that particular connection, be it what resource was actually requested, perhaps some metadata about that resource, referring back to an RDB paper, just describing what HTTP method was used or sent over this particular connection. And optionally, they may also want to link this back to a particular client. I should also note that in the real world, this is generally assumed to be studied in what we call the open world model, which is where you train potentially your classifier, whatever it is you're doing your initial preliminary assessment on a fixed set of connections, but what the actual clients do in the wild is sort of unpredictable, and so you're not constrained to that which you train your initial experiments on. So the closed world model, which is generally considered to be much easier in this particular problem space, and what we actually for this particular work studied, of course gives better results for classification and identification, but ultimately goal is to focus on the open world. And as was presented earlier, there are lots of different features available when you want to do this type of identification. Particularly, you can look at network addresses, you can look at packet timing and sizes and all these things, or even the clear text information that was previously available or is currently available, depending on what client software you're running. In this work, though, we're assuming that the things that should obviously be encrypted, like DNS and SNI, are encrypted. We're assuming that we're not, the adversary is not looking at packet timing and sizes, strictly looking at network addresses to try and figure out, what particular website or what service a particular connection is trying to access. So if you look at the sort of the spectrum of information available to an adversary wants to do this sort of fingerprinting. Back in the day, before we had anything from before we had HTTPS and encrypted DNS, everything was kind of centered on a clear text. It was very easy and hunky-dory for the adversary to just simply look at what the clients were doing. And as things have sort of become more and more encrypted, the features that are available sort of become a bit more difficult to act on. So right now, if you assume a world where we have encrypted SNI, encrypted DNS, you look at information available at the network layer, so IP addresses, you look at patterns in the traffic, and the goal is to strictly identify or fingerprint a connection based just on that information. And the idea of this is to try to show or claim that it becomes increasingly difficult as you obviously take away the clear text information on the wire. So the current state, assuming you're running perhaps some older software in resolving or opening up a particular connection, an HTTPS connection, you have a client in the middle who sends a clear text query to a DNS resolver, gets back an answer in clear text, obviously knows where they're going because they see both the query and the address. Everything's fine, at least from the adversary's perspective. And then he opens up TCP connection, TLS connection, everything again is exchanged to clear, and ultimately the resource that is thereafter is encrypted, but depending on the adversary model, again, they've already learned exactly what application the client is after. So it could potentially be game over at that particular point, especially if the goal is to censor based on that that signal. But if you add dot and do into the mix, and ESNI, lots more things are encrypted. But what remains currently, or as postulated based on the current designs for these things, are the ALPM values that are still sent in the clear in TLS, the IP address of the server to which you're connecting, as well as all the other network features that we mentioned earlier that I'm omitting. So we're focused strictly on the network address again, because that is the thesis is that is the sufficiently unique identifying information for the connection. So the experiments that were discussed in the paper basically worked as follows. Go grab a massive set of domains and write a crawler that goes and connects them, identifies all the the top level, the IP addresses that are resolved from trying, or that are returned from trying to resolve the top level domains, as well as the IP addresses for each sub-resource on a particular page. Do the resolution for all of those names to be at the top level domain and all the sub-URLs using ZDNS, collect all this data, and then try to see, how unique these IP addresses are. Seems fairly straightforward for this particular experiment. And if you look at the anonymity set that as results from that particular experiment, the data kind of suggests that basically there's many what we call unique IP addresses, those that fall into an anonymity set of size like 1 or 2. And this is not you may think it's perhaps uncommon as we move towards a world in which AWS and GCP and everything host a lot of applications. But still, there are a lot of there are older servers that run from behind a couch or have a unique IP address that simply looking at it can reveal exactly where you're going. So that's not great. But again, I take this with a grain of salt. This particular data is collected from closed world environments, so it would become harder to identify this or do this set in the open world. As we were saying earlier, if you look at, if you want to identify, for example, what is the actual page, a client is attempting to access, perhaps the logical thing would be to look at not just, a single connection that's initiated when loading that page, but rather the set of connections that are initiated when loading that page and all of its sub-resources. So as the on-path adversary, you see things like the DNS query patterns, you see TLS and TCP connection patterns. And the set of these things are often, should in theory be sufficient or more unique than each one on its own. So if you were to, as an example, if you loaded NewYorkTimes.com in Safari, you would see many, many TLS connections kicked off, many, many DNS requests sent over DO or DOT. And the union of that set is what we're using as the fingerprint for a particular page load. So the privacy of a page load then considers the same exact adversary, just assumes that the adversary is able to bucketize or group these connections from a client into a single event, and then use that to make a determination as to how unique a particular connection is, and perhaps use that uniqueness to associate it with known top-level domains. So the same features are available. We're just expanding the scope a little bit here. And that pretty much describes or shows what I was describing. So you go from a single connection to multiple connections, and you look at sums instead of individuals. Pretty straightforward. And same thing. So the experiments that were discussed in the paper, they didn't focus on the very large IP address set or domain set that was used for the single connection IP address anonymity experiment, but rather just the top 1 million, loaded them using their crawler, and then computed some basic statistics to see, for example, how many unique URLs are referenced upon loading each individual page. How many different domains does that kick off underneath the hood to see how many connections you're making. And the results of doing that, looking at the number of unique IP addresses, or the number of unique page load fingerprints that came out of it, is basically here. So you can see, if you look at the x-axis, the anonymity set size significantly shifts to the left, basically suggesting that by looking at the sum of these connections and grouping them into individual payloads, the anonymity set or the uniqueness goes up, which matches our intuition. Again, closed world, not open world. So still could be improved. So the conclusions we kind of draw from this very, very preliminary research, is still ongoing, is that clearly we need some sort of encryption of obviously clear text holes to get some sort of notion of connection privacy. And we need some sort of notion of connection privacy to get some notion of page load privacy. And I think perhaps that's like the ultimate goal of a lot of these things. I mean, encrypted SNI and DO and DOT are great in that they're focusing specifically on the connection privacy. But perhaps there's more that could be done to get towards the larger, bigger picture that we're trying to protect. There are a lot of related issues here and things that are potentially not considered in this experiment. In particular, like what if you have a client that's doing happy eyeballs to race connections across address families or even across interfaces? That might be worse in some ways because you're simply giving the network more information about where you're trying to go. So it's great for performance, as clearly demonstrated by all the clients that are implementing it and the benefits that it brings. However, from this particular perspective, it might make things a little bit easier for the adversary, which is not necessarily that great. However, on the plus side, the things that we're doing in like H3Biz to coalesce connections with secondary certs is great, because that potentially shoves more requests along a single connection and it's effectively removing information from page load fingerprints that would have otherwise, spun up new connections and perhaps added to the amount of uniqueness that exists for a particular page load fingerprint. Consolidation within a single CDN as well also helps, because you have single connections that basically clients are tethering to the CDN and then sending all their connections and all their requests over it. You can also do things like deploy proxies that hide the IP address, and that solves a lot of these issues, and perhaps that's even the most obvious way forward. And then there's also things that have sort of hurt us, especially with respect to ESNI, but in this case may help, and that is DNS load balancers that are constantly changing the IP address that you land on, so making it not easy to just identify a particular service by a specific IP address. I mean, you could do fancy things by potentially trying to identify the ASN to which that IP address belongs, and then associating, the IP addresses of particular connections with ASNs, and then looking at the union or the set of ASNs that result from a particular connection and using that to identify a PLF, but that has not been done yet. So perhaps that's an interesting or useful way forward. So I guess in general, the purpose of this work was to sort of show that the intuitive, it's a rather intuitive observation that yes, taking away clear text information from the network is a good thing, because it removes obviously the very clear privacy holes on the network, but there are still things that need to be fixed. But this particular problem, website fingerprinting based solely on address information, seems to be becoming harder based on the work that the IETF is actively doing, which is a good sign, I think. But then, reading back to the previous presentation, it's unclear what that means for the other side, or the other information that the adversary has available to them. For example, should they shift their focus towards traffic analysis, in which they are using information such as timing, inter-arrival timing, the sizes of packets that are sent, to sort of infer what the client is doing on the network. And this is something that Tor and the academic research communities have been struggling with for a very long time, and continue struggling with. Website fingerprinting just has a number of different papers, some of which we've tried to collate along with, in collaboration with Ian Goldberg, sort of a repository of all the known attacks in this particular area, looking at how bad traffic analysis is for non-Tor connections. Of course, much of the research is done in Tor, but it applies equally as well, if not more, to non-Tor connections, which don't do things like fixed cell padding to mitigate obvious or to make traffic analysis just a little bit harder. So I think next steps for this are to really kind of encourage people to take this problem a bit more seriously if they're not already, and that means like asking people to do more research in this area. Nikita and others are obviously doing it. We should implore them to keep going. I think documenting the known research that's been done in the area is also quite useful, if for no other reason, to having a single reference that we can use to either assess countermeasures, or sanity check to make sure or to learn whether or not something that hasn't been done actually indeed has been done. And then perhaps either IRTF or the IETF can work with these people who are actively working on these problems to develop mitigations to see what's effective, and from a cost performance perspective. So for example, the previous presentation, we got good results from sending DNS over Tor, but it's there's a performance hit there. So finding that right trade-off is difficult, and so perhaps something we should implore IETF and IRTF to be working on. So that's pretty much it. Happy to take any questions.
Yeah, we have 1 minute for questions.
You guys think I'm quicker than I am, I think. Hi, Chris. Dave Plonka, Akamai. Thanks for presenting this and presenting something different about it than what was at ANRW. I was afraid it was going to be the same thing as we were talking. The couple of things I wanted to mention, and you can figure out if they're questions or just comments. I've been working on anonymity sets on the client side instead of the server side so that we can report on activity in the web based on clients. And what it struck me from what you've shown here and from what the page load combinations show is clearly the solution for creating anonymity sets based on aggregation on clients that are very different than the server side. So it's completely complementary to what we're doing in MapRG. And then this last hackathon, I was writing code to do the anonymity.
I know, I saw that, yeah.
So, and we're going to talk about that on Friday morning. So, you know, whoever wants to work on this, let's get to talking about that. And then, well, I'll stop because I lose my minute.
I won't be there for MapRG, but I'll sync up with you and we can talk about it perhaps afterwards. Riyad?
Hey, Chris, Riyad. Just a quick thing. Can you go back to the second graph that you showed us with the buckets? So from this, it looks like anonymity set of 2 is 2 orders of magnitude smaller than anonymity set of 1. So if we sum up everything, that means that like 95% of websites can be identified with this?
Yes, it was a very high number.
Thank you.
Hello, Tim Costello. Thank you very much. That was
So
very
just
good.
2 more quick questions.
You mentioned load balancing in there. Were you saying that load balancers are an adversary?
No. Just that DNS-based load balancers might give you different IP addresses if you try to resolve the same name over and over again. So a simple, you know, a naive approach to trying to map name to IP address and looking at the first result that comes back might not always work because the answer will change. Yeah, Nick.
Nick Sullivan. So, Chris, what about the children? No, but seriously, this is dealing with passive adversaries. Yeah. Have you thought of adversaries that are more actively trying to subvert such types of anonymity protections?
No, not yet. I'm hopeful that Nikita and the group that's working on it can, you know, start taking that a little bit more seriously. Yeah.
Sorry, Dan, we don't have any more space. Really sorry.
Sorry. We can talk offline if you wish.
And the mailing list also.
Thank you.
Thanks.
All right, my name is Rowan Freshbeck. I work for Untitled Labs. This is joint work with Gijs Reinders, who was my master student, Matthijs Monhoff and Luca Lodi from Tesorion and the Technical University of Eindhoven, respectively. Right, so it feels like we're repeating ourselves here because I think somebody had a similar slide and the person before me had a similar slide, and the IETF is focusing on protecting people's privacy, which is great. We have things like dprive, we have DNS over TLS, we have a lot of buzz around DOH. But the focus of all of this is mostly on privacy of traffic in flight, right? So we're trying to protect traffic from adversaries that are on the network. But if you look at the domain name system, there is a sort of an obvious elephant in the room, which is the operator of the resolver that even if you protect all of the traffic in flight, still has access to your traffic. And they might actually have legitimate reasons for doing so, right? If you are an enterprise network, you may want to use DNS to detect indicators of compromise, so people that are infected with malware on your network. Or you want to be able to monitor threats in large user bases. For example, Quad9 does that. They have a very strict privacy policy, but they still inspect traffic in order to detect malicious behavior in larger populations that use their resolver. So it is probably too easy to say they shouldn't do this, but what we wondered is, can we find a better way of doing that sort of provides some privacy guarantees for users when we're inspecting traffic on the resolver itself. So what we did is my master's student developed a potential solution for this, which uses something called, that is called Bloom filters, which some of you may be familiar with, but I will explain it in the next couple of slides. More importantly, we have a working prototype, which is open source. The URL is on one of the last slides if you want to have a play with it. It's very much a prototype, but it gives you some idea what it does. And we tested this in production at SurfNet, that's the National Research and Education Network in the Netherlands, on resolvers that have a client base of roughly 200 to 250,000 users. Right. So
first up, Bloom filters. So Bloom filters were developed in the 1970s to basically they're a method to speed up database lookups. And they are a highly efficient mechanism. So insertion and lookup is roughly order 1. And basically you can think of a Bloom filter as a probabilistic set. So if you have an element n that has may or may not have been inserted into the filter, then and if you query a filter, then if the filter says it's not in there, then it's guaranteed not to be a member of the set. If it says yes, this is a member of the filter, then there is a small probability that this is a false positive, but it's highly likely that that particular element is in the set. So how does this work? You take, for example, a domain name, you run that through a set of hash functions, then you get some output. This is actually the SHA-256 hash of that particular domain name. You use you use parts of the hash or the different hash functions from multiple hash functions as indices in a bit array, and then you flip the bits to 1 if at that particular index. So on the left-hand side, you see insertion. So we insert example.com and example.org here. As an example, this is a toy example with only 8 bits in the bit set. And then if you do a lookup, you go through the same process. And if there is at least 1 bit set to 0, then the element that you're looking for is guaranteed not to be in the filter. And if all of them are set to 1, then it is either in the filter or it was a false positive. Right. So with a Bloom filter, you basically have a trade-off between the false positive rate and a reasonable filter size. So you don't want to have huge filters, huge bit sets that you need to keep in memory, but you also want to keep your false positive rate relatively low. And the parameters that you use for that is the number of hash functions that you use, or rather the number of indices that you extract from the hash to sort of flip bits in the filter, the size of the bit array, and the expected number of elements that you expect to insert into the set. And then the formula on the slide gives you a rough estimation of the false positive probability. Now, the idea that we had was that what you could do is to take all of the queries from your clients and insert these into a Bloom filter. And this is actually interesting. This is a methodology that's already used to find things like newly observed domains. For example, I think Power DNS has an implementation that does that. But what we wanted to do was use this information to check if a name was queried for, but we're not interested in by whom that name was queried for and exactly when. So what we want to do with this is to perform network level threat monitoring. So we say that we have a domain name that we know is malicious. We want to be able to say within a certain time frame, did anybody ever query that name in our network? And the Bloom filters give you some nice properties with that because they are non-enumerable. As soon as I've inserted something, I have no clue what I inserted anymore because it's turned into a few random bits that I flip in a filter. If I mix queries from lots of users into a single filter, it becomes really hard to sort of distinguish queries from individuals. What is also interesting is that due to the mathematical properties of Bloom filters, we can actually take multiple filters and combine them into a single filter, which has a higher false positive probability, but contains more data and thus anonymizes even more. So the prototype that my student developed does is that it has a sort of an auto-tuning mode that you can run it in against your resolver for, say, a few days to see what your query pattern looks like. And then it will suggest Bloom filter parameters that you can set in order to have a certain false positive probability. So we, for example, want to do hourly filters in our experiment. And we want to be able to aggregate these to single day. So we want to combine 24 hourly filters into a single filter for a day when we do aggregation. And we would like to have a false positive probability of 1 in 1,000 for the daily filters. And what the graph shows you is that it's important to do the tuning, because if you look at the number of distinct query names that you see in a day on a resolver, then on an hourly basis, it's the red line. So that's anywhere between, so it's roughly 4 million distinct names within an hour that we see. But if you look at this on a daily scale, then the number becomes much higher, and you see roughly 30 million distinct names in a single day. Now, the future extension that we want to do is that it keeps automatically tuning. So what it will do is it will ensure that all of the filters for a single day can be aggregated, but it will use the predictions from the previous day to set up the filters for the next day, so that you don't have to constantly manage the system. So what do we put in there? What we wanted to be able to do, so SurfNet is a large research network. It has many universities connected. It has schools connected to this. And what we wanted to do was to be able to distinguish queries from different institutions, but not from different users. So basically the things that we insert in the filter on the slide. So if we have, say, evil.domain.com, then we will insert both the second level, all of the labels, but also organization A at evil.domain.com for the specific network that query came from. This means that if we want to say we get an indicator of compromise, we want to work out if that indicator of compromise was ever seen on the network, we can put it in the Bloom filter. It will tell us if it was seen, and then we can sort of enumerate over all of the institutions that are in there and figure out which institutions sent us that query. Now, we tested this prototype for about 3 weeks on a busy DNS resolver. This shows the query pattern in queries per second for that particular resolver. And we studied 3 use cases. I'm not going to go over all of them because that would take too much time. I'll refer you to the paper. There's a link on the last slide to the paper. But what we looked at was detection of so-called booters. So these are DDoS as a service website. We looked at hits on email blacklists, and the one that I'm going to talk about is the National Detection Network. First, a little bit about the predicted versus the actual false positive rate for the filters. So we ran auto-tuning for a week before we did our experiment, and we chose as filter parameters that we would set 10 indices for every query that we get, and the bit filter size was 491 megabits, as it's roughly 59 megabytes in memory. So that's actually quite reasonable if you compare the resolver cache on that machine, which was about 2 gigs. So our goal was to keep the daily false positive rate below 1 in 1,000. And of course, we had to estimate the number of elements that we inserted. So this was sort of a little bit of hand waving. But after you've used the filter, you can calculate the actual false positive probability, which is the formula is given there. It's explained in the paper. And for the life of me, I can't remember what S is. But the graphs show you the result. The black line is 10 to the minus 3, so that's 1 in 1,000. So anything above, so the graphs are a bit confusing. Anything above the red line means we had a lower false positive probability than we actually set. So the takeaway from this is that we actually had a very good false positive rate on the Bloom filters. And then especially if you look at the hourly, because we use the same parameters for the hourly and the daily filters, otherwise we can't aggregate them, then of course at an hourly level, the probability of a false positive is very, very low. Now, one of the things that we tested this with is the National Detection Network, and this is something that is managed by our government, the Dutch National Cybersecurity Center. And what they have is they have a system that runs a MISP, so it's a Malware Information Service Platform, I think is the acronym. And what they put in there are high-value indicators of compromise. For example, indicators of compromise that come from the intelligence services. Now, and the condition for participating in this national detection network is that you don't just take data from it, but you also put data back into it. So say you get an indicator that there is some malware active, then what they want to know is, how does this affect your community? Because their goal is to figure out how Dutch society is impacted by these threats. Right, and of course, SurfNet wanted to participate in that, but they didn't want to monitor all of their individual users. They didn't want to throw away the privacy of all users in order to participate in something like this. So this particular solution that we implemented was very interesting for them because it allowed them to take the indicators of compromise, hold them against the Bloom filters and figure out if there are hits on that, and they could report it back to the National Detection Network, but they also got some indicators of sort of what threats there were in the network. The graph shows you the number of threats that occurred on a daily basis. So it's not a huge number of threats. It's in the order of 40 to 50 unique threats per day. But the interesting thing about this is that Surfnet's privacy policy prevented them from monitoring individual queries. So they couldn't do this before. And now that they had the Bloom filter solution, they could do these lookups and actually work out whether these threats were occurring in the network. And we found an actual compromise, which was a WannaCry infected machine. So what we did is, as soon as we found out that one of the threats that was detected was WannaCry, what we did was go to Surfnet's privacy officer and say, hey, we found this threat that maybe needs mitigation. Can we now specifically monitor for this threat? So rather than doing blanket surveillance, we can look for a specific threat and then see who is infected and chase up that machine. So this is much less invasive for users than just sort of monitoring all of their traffic and then just telling them, no, we're doing this for your good. No, in this case, we can make a balanced decision whether or not to monitor for something or not. So some other benefits, no personal data is stored, of course, because we don't retain any IP addresses. This is aggregated at the individual network level. But this means that you can retain this data much longer, which allows you to do historical lookups, which is very interesting. Think back to, for example, the WannaCry case, where you could recognize that this threat was present on your network because it would do certain DNS queries. If we had had this running at the time, sort of before that threat existed, as soon as the malware researchers discovered that particular query, we could have gone back in time and worked out when is the first time that we actually saw infections, which is something we can't do right now. And that would be very valuable for threat intelligence. Another thing is that, and this is something I as a researcher find very interesting, is that you could share this data with third parties without disclosing PII to them. And then they could, for example, say you take filters that are collected in different networks, then you can do co-occurrence of queries. If and say, I found this query that I think is malicious, which other networks did I see that in? And was that roughly at the same time? And the final thing is that as a nice side effect of how Bloom filters work, you can do cardinality estimates, or the number of distinct queries that are in there, you can estimate that because it's sort of related to how hyperloglog works, if you're familiar with that. Right, so the prototype code has been released as open source. The URL is on the slide. So Surfnet, where we trialed this, is planning to take this into production because they want to use this for their CSERT team. And at Edn Labs, we're creating the tools to integrate this into our open source products, in particular our Resolver product Unbound. And the goal of that is to, again, release this as open source software and make this really easy to deploy, so that if you want to do this kind of network monitoring, then at least you now have a more privacy-friendly solution available than just blanket recording every query that all of your users make. And I hope that it's a little bit of proof that security and privacy can go hand in hand. And with that, this is the paper. The link is on the slide, and the slides are up in the data tracker if you want to read the paper. Are there any questions?
Hi, Roland. Dave Planka. Super cool work. I can't wait to read the paper. The question I have is about the sharing. Are you comfortable giving out your full Bloom filter to the NCSC, or I can't believe they would give you their Bloom filter back? How does this sharing really work?
Okay, so for the National Detection Network, Surfnet is certainly not sharing the whole Bloom filter with NCSC. What they are sharing with NCSC is if there are the detections that they do themselves. So say I have a threat, I detect that, then we report back, we saw this threat in universities or in, I don't know, schools for vocational education. But of course, it's not the Bloom filter that they're sharing. What they're sharing is whether or not a threat was detected.
But don't you have to take the coincidence of the Bloom filters to find out if the one Bloom filter had the vulnerabilities or the attacks that were represented in the other? I'm not understanding.
Sorry, I can't hear you. Can you step closer to the mic?
Oh, I was just saying, don't you? It's the coincidence, the Bloom filters, that shows that there's evidence of those attacks or vulnerabilities in one set.
Yeah, but so
who's the one that's finding the intersection of the Bloom filters? Because that's the one you're trusting, right?
So I think you're sort of conflating two things. The idea is that the network operator, in this case Surfnet, who participates in the National Detection Network, does detections on their own Bloom filters that they record on their resolvers, and they just report infections back to the cybersecurity NCSC. They don't sort of send the Bloom filters there. What you could do, a distributed model, is that you could have a query API where somebody could send in, say, has this name been queried? Is this name present in your Bloom filters? And then you do the lookup and you report yes or no.
I agree with you that if you have the remote query, that's a way that you could possibly share. But if you give the Bloom filter, then they can query ad hoc.
Yeah, they can query ad hoc. Yeah, correct. But so I wouldn't advocate giving it to something like NCSC. But for example, say you have a university researcher who is interested in this, then I can definitely see conditions under which you could share that data with them. Yeah.
Hi, Kirsty P. from the NCSC in the UK. Thank you for your presentation. I found it really interesting, and I think it's a good piece of research that needs to happen in this space. And like you said, it's nice to see that security and privacy can go together. I just had a question on your previous slide, I think maybe the one before, about, oh, maybe it was a couple ago, sorry. Yeah, about sharing the Bloom filter with third parties. So in this case, I would just be concerned about the potential leg up that you would give a threat actor in knowing that their domain or whatever was noted and they could just change their techniques. So threat intelligence is shared under the TLP protocol at the moment. And yeah, just to say, when you share it with researchers, I worry about giving it to any academic that, you know, fancies it.
So of course, when I say sharing with third parties, it should have a little asterisk that says under certain conditions, right? I am an academic researcher, so I don't worry so much about sharing this with academic researchers. I mean, trust me. But you do have a point, right? You want to have certain safeguards in place before you share this kind of information. I guess it also depends on the network that you collect this information in. SurfNet is a research network, so there is one of the goals is also to do research on the network itself. So if you share that with researchers that are within say their constituency, then there could be good conditions for doing that. And actually, SurfNet has a data sharing policy that sort of lists conditions under which this kind of data can be shared with researchers. And then there are data sets that can be shared with researchers within their constituency or random academic researchers around the world. And I can't speak for them, but I would say that this is data that they would definitely feel comfortable sharing if the conditions are right. Because I talked to their privacy officer, and she understood this really well, quite well, even though she didn't have a technical background. This was sort of easy to understand, and her intuition was that, for example, this would not be subject to the GDPR because of the data that gets put in. And that meant that under certain conditions, we could share the information, even though there are some privacy risks if you can just try and send whatever question you have to the filter and figure out if something's in there. Does that sort of answer your question? Sort of, okay. Any other questions? Okay, thank you for your time.
Thanks, Roland.
Oh, yeah, sorry.
No, thanks.
Okay.
Thanks to all our presenters. Can we have a round of applause for all of them, please? Thanks. Do we have the blue sheets? Has anyone not signed the blue sheets? Where are the blue sheets? We shall be moving on to the internet drafts. Is Roland, sorry, is Fernando online?
Hi there, can you hear me?
It's really low.
Okay, I will try to speak closer to the mic. Is that better now?
Yes.
Okay. So I'm Fernando Gont, and I will be presenting a set of 3 documents to our target at PEARG. These documents are about the security and privacy implications of numeric identifiers employed in network protocols. These are a set of documents that we have been working on for a few years now with Edn Airspace. Next slide, please. So as an introduction, essentially, for the last 30 years or so, we have got the topic of numeric identifiers wrong in many protocol specifications and implementations. As
Fernando, you're
examples,
breaking up.
you may recall. Yeah, let me. Maybe this is better. For example, you may remember issues that we have faced with TCP initial sequence numbers, predictable transport protocol numbers, predictable IPv4 and IPv6 fragment identifiers, predictable IPv6 interface identifiers.
Fernando, your audio is really scrambled. We can't make out anything.
Okay.
Yeah, I think he disabled video.
I did. Yeah. I don't know if I can disable. Let's see if I can disable. Yeah. Let's see if it's better now.
Could you try
okay.
again?
So essentially, lessons that we learned with, with identifiers of some protocols, essentially were not applied to other protocols. So it's essentially the same problem that repeated over and over again in different implementations and in different protocol specifications. Next slide. So essentially, we work on a set of 3 documents. These 3 documents used to be a single large document, and based on the advice on a number of groups, we split this document into 3. The first document is, numeric IDs history, in which what we try to do is cover the timeline of some sample numeric identifiers. This document targets PEARG. Second is about proposing algorithms to, to generate these numeric identifiers, without or avoiding the security and privacy implications. And the third document is a document that we hope can be published as an AD-sponsored RFC, which essentially tries to force protocol specification writers to have to do a proper analysis about numeric identifiers. Next slide. So the first document, numeric IDs history, essentially what we do, we cover some sample numeric identifiers, IPv6 interface identifiers, IPv4 and IPv6 fragment identifiers, and so on. And what we try to do with this work is essentially to illustrate, how essentially we face the same problem over and over again, sometimes for the same identifier in different protocols, like fragment identifiers in IPv4 and IPv6, or sometimes it's the same problem at the end of the day, but for different protocols. This document, again, is targets PEARG. Next slide, please. The second document, it's a little bit more complex. Essentially, what we try to do is to categorize numeric identifiers based on their interoperability requirements and their failure mode. Interoperability requirements are requirements that must be complied to based on the protocol. There are different sort of requirements like uniqueness, an identifier that must be monotonically increasing, and so on. And the failure mode is essentially, what happens if you don't comply with those requirements? So based on those categories, what we did is, try to go through most of the numeric identifiers that we are aware about and try to see if we can make each of them follow into one of the categories that we define. And for each of those categories, what we do is propose some sample algorithms that can comply with the interoperability requirements while avoiding the negative security and privacy implications of some known algorithms to be flowed. As the previous document, this document targets PEARG, so this group. Next slide.
Fernando, your audio is giving way again.
Next slide.
I think given the lack of time, we're just going to move on to the next. I'll just go over the slides, Fernando. And I think this draft, the third draft, which is, I think is under consideration for AD sponsorship by Ben Kadek. And we spoke to the security AD, Ben Kadek, and also the authors of the draft, the two drafts. And it seemed like the first two drafts, history and generation, were under scope for and could benefit from coming to PEARG. And we were thinking of adopting them. So do people have opinions on this? And we're looking to do a hum at the end to get a sense of whether the room is okay with us. There's consensus to adopt these two documents. So if you have comments, please come and speak.
How many people have read these documents? Show of hands. Only a few. Okay.
Does anyone have opposition to the research group adopting these documents?
What's the research content?
So say that again?
What's the research content?
I believe history and generation are the two drafts we were talking about.
I'm sorry?
So one of them is just the survey, basically, of all the past
Sure.
problems.
I've read them. I'm saying
I don't know what the research,
Yeah.
the actual research content of the generation. Hopefully Fernando can answer us, so I'll let him into the queue. Fernando?
Yeah, sorry, the connection was lost. What was the question that I was meant to answer?
Fernando, can you answer on Japper? Should move forward, come back to us.
Yeah, I guess in the interest of time and due to the technical difficulties, we'll just move on to the next presentation and come back to this question at the end, if time permitting. Of course, we can always take this to the list afterwards. So on that note, David Oliver. Excellent.
Hi, I'm David Oliver with the Guardian Project, and I'm going to talk about an internet draft we've submitted recently on enabling network traffic obfuscation via pluggable transports. So first of all, what are pluggable transports? Mechanism for enabling the rapid development and deployment of network obfuscation techniques used to circumvent surveillance and censorship. The details about this work, which has been going on for some now, are available at this URL. The generalized architecture here is that there is a server that's exposing a public proxy that accepts connections from pluggable transport clients. The client transforms traffic before it hits the public internet. The PT server reverses the transformation and then passes the traffic on to the server app. There's also an optional lightweight protocol to facilitate communicating connection metadata. So when you're migrating between one connection type and another, for example. So since we don't want to limit the behaviors of what pluggable transports can do, this idea focuses on the interface between the technologies and the applications themselves, not on what goes on inside of an obfuscation technique. The draft that we've put together is based on the Pluggable Transports 2.1 specification, which is a work of a fairly large and diverse community of people, and it has two subsets. One is what we call the Transport API interface, and the other the Dispatcher interface. So one that is focused around in-progress language-specific API that's integrated directly into the client app on the client side and into the server app on the other side. And communication within the app, or the way the app on both sides sees the pluggable transport, is like a socket. With the Dispatcher API, this is to be used between processes. So there's another process on each side that handles the process of obscuring and unobscuring, and passes so that the actual application doesn't have to deal with that aspect of the problem. The dispatcher here can be configured with different types of proxies, so you can have live at any moment different kinds of transports available that are connected to different kinds of proxies and can respond to different kinds of traffic. So this is sort of that architecture described in graphic form. Here's the transport API, where what's going on in the transport's actually bundled into the application itself. And here's the case with the dispatcher, where the actual applications don't take part in or haven't got compiled in the kind of obfuscation technique being used. And here's a case where there's a mixed architecture, where maybe the client uses a dispatcher type environment where the server has a transport style environment. The spec also talks, or the internet draft also talks about where we can, looking at the older specification, which was just the dispatcher API, and the issues related to linking across language, and then also this idea of adapting back and forth between types of technique. And I think that's it. Questions?
Ben Schwartz, what would you like to see happen with this document?
Well, yeah, I guess I can give maybe my own personal response to this, because I'm not sure overall myself. But there's been a lot of work go on in this area, and it is, in my mind, sort of occurs in user space of necessity, because we want these techniques to be adapted in a very rapid way. So it's unclear to me what, or it needs to be debated what sort of final position this has in some standardization work. Should some of this stuff take place lower in the network stack or not? And if so, why? And if not, why? Etc. But we do hope this work took place for a limited period of time, only within sort of one small set of the community. And now we have a larger community that finds this interesting. So there seems to need to be some bridge between some long-term standard and some just lack of unity on the topic.
Thanks.
How many people have read this document? So only two.
Thanks for your question, then, Ben.
I'm one of the authors.
Well, of course. Yeah, I think this certainly needs, I guess, more review and reading from people here. If you find it interesting, please send comments to the list, and then we can kind of decide what to do at that point. It's certainly very interesting work, but it might be a bit too early at this time. So let's get more feedback on it first. Thank you, David. Hey, Joe.
Stand here? Oh. Hey, so I think I have 3 slides. The first time I presented this was in November of 2014 in Hawaii. You may or may not remember it. It's been edited a lot. It's been refactored to reflect a network structure. It's accredited authors. We had Nick Feimster and some students at Princeton help with it. It adds more modern things like blocking of ES&I in South Korea and stuff like that. The reason it hasn't gone very far is because I'm the one working on it, and I diverted my efforts, which is, I don't have a lot of time for IETF work, to the IS 2.0 restructuring work, which is recently done. Yay. So I'm doing a lot more stuff that doesn't involve administrative stuff. Just a real quick overview, 10 seconds. It orders the discussion about censorship around 3 things. Prescription, that is, what do you want to block? Identification, how do you technically identify those things that you'd like to block? And then interference, the actual performance of the blocking. There's a ton of small and medium issues that a bunch of people have identified in their reviews that are in our issue tracker. We're going to be going over those in the next couple of months and incorporating all that good feedback. And since this is possibly a research group draft, we're going to actually try and do some outreach to areas that haven't gotten much review of this. So routing and DNS in IETF, just to excerpt the chunk of it that's there and see if we get additional feedback there. Although some people like Stefan a long time ago reviewed an earlier draft of this. The bigger issues that have been talked about on the list, there's this thing about mitigations. I was initially pretty, so just to state the problem, some people feel that it would be a better draft if it actually, in addition to describing censorship techniques, it included discussions of mitigations that may or may not be relevant for each technique. I was initially pretty reluctant to do that just because it felt like it would blow up the draft, but I should say I can go either way on this in the sense that I think pithy statements under each technique that describe some types of mitigations may work. I think the trick is that censorship techniques change quite a bit. Mitigations change in my totally just ad hoc or intuitive nature. They change even more quickly. Some things like domain fronting, come and go, right? I forgot his first name. I should know it. Vittorio Bertola said specifically that censorship may be too negative of a framing. I come from a digital rights background where we talk about when someone's blocking something you want to get access to, that's censored no matter what it is. Happy to say blocking techniques. Do you want to talk now?
Whenever you're ready.
I'm almost done. There's a chunk about non-technical forms of prescription and interference, so ways of finding stuff and blocking them, like self-censorship or legal mechanisms and stuff like that. I'm not wedded to that stuff. It just felt like it would make the document sort of complete, and it's sort of the rubber hose thing that might come into play in certain kinds of things. And I thought like some rough description of what that rubber hose might look like. There's the bigger issue of this stuff moves really quick. It may need to be a regularly updated draft. I know that that's a different discussion in other places. Some people don't care about that. Some people feel very strongly about that. It may be something we want to wait for the living standard discussion. What's the research content? It's sort of, you can think of it as a review article, a systematization of knowledge. There are some gaps in certain areas that we're working to fix. And then one other thing that I wanted to say that's escaping my mind. No, I'll stop.
Perfect, scrolling. So first of all, you should call it SOK1 rather than RFC something.
Cool.
More seriously, on this question, should be a living, updated draft. I guess that's a question for you: is how often do things change? If things change, on the scale of every 2 years, then just publish this one and then publish another one in a couple of years. If they change every 2 months, then probably that's so awesome. So I think it's really a question for you rather than for me.
It's not a constant rate of change.
Yeah, sure. I'm ambivalent on this non-technical thing. The censors, like the framing thing, like the reason censorship has like a bad name is because people don't like censorship. Yeah. And if you call it WBT, people will soon call it WBT will soon be a bad word and we'll need a new name for WBT. So no, I think you should stick with censorship.
Yeah, and what I thought was if we change the title and everything throughout to a survey of worldwide blocking techniques, that doesn't make me feel too bad.
I can live with that, but it just seems like this newspeak, right?
Mallory Noodle, Article 19. Since we're solving all the bigger issues on this slide right now, I think for the first one, maybe this is a question for you, Siobhan, it seems like in the charter you are open to talking about threats, not just mitigations. And I do think that censorship and privacy are two sides of the same coin. So I don't know, maybe we can talk about that more because I feel like it would fit within the charter. I was just rereading it before I came up to the mic.
Yeah, agreed. That was more of a suggestion than a statement, I think.
Sorry.
That's all right.
Email sucks, right?
Wendy Seltzer, thanks for this work. I think the non-technical forms is a valuable addition because we're always thinking about where is something going to get routed if the technical means aren't available. And thinking about that sort of broad piece of the threat model is helpful to thinking how effective are anti-censorship mechanisms.
Thank you. Stefan.
Stefan Bartsmeyer. Regarding the first point, the fact that the draft is still not published as a RFC show that it's complicated to keep this sort of thing up to date. I vote against including mitigations, because the big problem with mitigation is not only that they evolve very fast, but also that can have consequences. Bad advice can be really harmful for people. They can, for instance, show that you try to walk around the censorship, things like that. So it's much more touchy. So I suggest to stay with threats only. And of course, to call censorship, because otherwise, people who censor don't want to be called censors, but that's what they are. So just use plain words.
I hadn't thought about that. If we put a mitigation here that someone uses, then they end up in jail, man, I'm going to feel like really bad. But anyway.
Thanks, guys. Is that a question? Oh, sorry. Yeah.
If you're still looking for inputs on this.
Oh, absolutely.
For the first one, I'm not sure how much beyond RFC 6973 will be able to contribute, even if we go down the path of including mitigations. So that's, I mean, personally, I'm fine with the contents as they are. On the second one, I don't think there's a need to change it.
Okay.
Yeah, but maybe the title should reflect the scope, which is that this is not all online censorship. It's just internet traffic and website censorship. So maybe that just fixes it.
That's a good point.
Are people...
Sorry. I'm the JavaScript, so I'll write it, but Gushabadrova, I forgot that.
Thanks. Are people opposed to adopting the draft as is? Does anyone have any comments on that? Okay. And have people read it? See a few hands. We're going to do a hum on adoption of the draft as is. So if you're in favor of adopting the draft, please hum now. If you're opposed to adopting the draft, please hum now.
All right, yeah, so it sounds like we have positive support for it. So we'll confirm on the list and go from there.
Thank you, guys.
Excellent, thank you, Joe. Just to be clear, the question of how frequently the document will be updated, as you said, does kind of bleed into the living document issue. So we'll discuss with Colin what is a good strategy for dealing with that should the adoption happen. But for now, the normal thing will happen, I guess. Right. So this brings us, I guess, basically to the end. We had to cut Fernando off earlier because of technical issues. Were you going to say something from him? Okay. Yeah, please.
This was a response to Echo's question earlier, which was on what were the research questions in the draft? Yeah. And Fernando said, identifying the reasons for flawed IDs, categorizing them based on interoperability requirements and failure modes, and producing algorithms to address such requirements.
Yeah, I guess we can take that question also, that question of adoption for that also to the list then.
Yeah, that sounds good. People, please read the drafts if you're interested in it, and yeah, we'll ask whether or not people are interested in adopting it on the list and go from there. I think at this point, perhaps, given the few number of people that have actually read it, doing a hum here is perhaps not the best thing. So we'll just take that one to the list. And with that, unless there's anything else, we can end a few minutes early. Thanks, everyone.
Thanks. Where are the blue sheets? Okay, thanks. I guess I was probably.
Hi, I'm Jan. I had a question regarding the work on the set of the you usually
Yeah, we're trying to do basically we're on this board. So basically fix it up but not always. Yeah. That's a very good suggestion. Yes.
Also, another nice source for the next thing is the CT logs.
Yeah, so we're using that. We'll see if you want to tell that.